How's it going, ladies and gentlemen? Mr. Johnny here again, looking at 17.5 factors that affect solubility. So the first question, the molar solubility of which of the following is not affected by the pH of solution? So it's important to look at, well, what's going to happen when we put these things into solution? Well, we're going to get Na+, which if it were to react with water, it could make NaOH, which would be a strong base. And we're going to get PO4 -3, which does a really good job at picking up hydrogens, right? So this is actually acting as a base, and it's going to be picking up hydrogens. So the pH would affect the solubility of this thing, because as we change its pH, well, if we were to make it more acidic, we'd be able to dissolve more PO4 and therefore more of that stuff. All right, so now if we take a look at LiF, well, what would happen? We would get Li positive, which could react with water to make LiOH, which would be a strong base, and we would get F minus, which would react with water and say, hey, I like taking up hydrogens because I'm the conjugate base of a weak acid. So we would get a weak acid. So we have a strong base and a weak acid mixing so the pH would affect it. Right? If we had a higher pH, or I'm sorry, a lower pH, more acidic, we had a lot of H pluses, we'd be able to pick up more of those F minuses and we'd be able to dissolve more LiF. All right, so now if we take a look at NaNO3, well, that's like when it dissolves, it can make an NaOH, which is a strong base, and it can make an HNO3, which is a strong acid. So basically, these ions are not going to interact with water. The strong base, Na is not going to want to pick up an OH minus because it gets rid of it right away and ionizes completely. NO3, same deal. It's not going to hold on to an H because it's a strong acid. It's going to let go. Whereas if we were to look again at like the PO4 -3, when you put it in water, it's going to hold on to hydrogens. It likes to hold on to a few hydrogens. So it's going to be affected by the pH. So the NaNO3 won't be affected by the pH. Let's check this one out. MgOH, well, that's a strong acid, so it's not really going to hold on to the OH minus. So pH won't really affect the solubility of the Mg+2 ion. But we're also going to get S-2, which is the conjugate base of a weak acid, right? The S-2 likes to pick up a hydrogen and become S-1, which is, it can still pick up another hydrogen, become H2S, which is a weak acid, which means it likes to hold on to those hydrogens. So that means the S-2 is going to be looking for those hydrogens. Like, hey, hydrogen, I'm holding on to you. I'm going to hang out. And hydrogens, that depends on pH. So this MgS would be affected by the pH. So you got to take a look. Well, how are these ions going to interact? Is it going to pick up an OH and hold on to it? No. Then it won't be affected by pH. Is it going to pick up an H and hold on to it? No. Then it won't be affected by pH. If they would hold on to one of those ions, then pH matters. So we take a look at number 2. It says, which of the following aqueous solutions would you expect AgCl to have the lowest solubility? So if we're talking about low solubility, that means we already have a lot of Ag+, or we have a lot of Cl-. So we're looking for the one where you're going to have the most of either. So if we take a look, the first one, pure water, that doesn't have either. That's not going to work. We have 0.24. Did I leave off units? That should be molar. 0.024 molar KCl. So you get 0.024 Cls. 0.025 NaCl. So you get 0.025 Cls. 0.03 AgNO3, so you get 0.03 Ags, or 0.02 BaCl2, which means you get 0.04 Cls. All right, well, that's going to affect it the most. It's going to decrease the solubility the most because there's the most common ions, most amount of common ions in choice E. So choice E would have the lowest solubility for AgCl. Now, the next question is a little bit easier. Which of the following would you expect to have the highest solubility? So that means, all right, well, if we got Cu and Br, we want the least amount of Cu plus and the least amount of Br minus in that solution, because that means we have less common ions competing for solubility. Think of it that way. Well, pure water, you can't get lower than 0. So pure water would have the highest solubility, right? Yep, there you go. 4. What is the maximum concentration in molar of silver ions in a solution that contains 0.05 molar CO3 minus 2? We give you the KSP. So remember KSP, well, if we got Ag2, that's going to be Ag plus squared times concentration of CO3 minus 2 to the first, because you only get one CO3. All right, and they want to figure out the maximum number of Ag plus. All right, well, we know CO3 already is, 0.05. And they want to know, well, what is X? And that's going to be squared. So now we just got to, do a little algebra. You get X equals the KSP divided by 0.05, and then that whole thing is square rooted. So that we get X by itself. So now it's just a plug and chug, right? And we get beep bop, boop. 1.27 times 10 to the minus 5. All right, number 5. What is the solubility in molarity of PbCl2 in a 0.5 molar solution of HCl? KSP is as follows. All right, well, they give us the HCl, and the reason that that's important is because of that Cl, we got a common ion. And they tell us the KSP of PbCl2. So let's figure out the expression. We're going to get 1 Pb plus 2 ion, so it's to the 1 power. And we're going to get chloride ion, and we're going to get 2 of them, so it's squared. Now, molar solubility for this, let's think about this. We start with no Pb, and we're going to add a certain amount. So we're going to have X amount. The chloride ion starts with, what's it say, 0.5, so let's make this a 0.5 molar, and it's going to get X amount more chloride ions for every 2X more. Because let's think about this. We got PbCl2, so for every Pb we add 2 more Cls. Now, this would make math really, really complicated. But we can do something which you guys are going to start to love. We can assume stuff. Let's assume that X is so little, which is kind of a safe assumption looking at the KSP, that 0.5 plus 2X is still going to equal 0.5, because we're going to say that X is small. No, we're not even going to say that. We're going to say it's tiny. No, we're not even going to say that. It is minuscule. Hope we can spell, compared to the 0.5. And that's something we can check after we do the math. So we're going to say, you know what, that's going to be so small that it doesn't even make a difference. So now we can pretty easily solve for X. So we do some algebra. We get X equals KSP over 0.5 squared. And we get a value of 0.00064. So now let's see, is that assumption safe? Well, we had 0.5 molar, and we're going to add twice this. So we're going to end up adding 0.000128. Now, if I were to add 0.5 to that, it's going to round to still be 0.5, right? Because our rules of sig figs and precision, it's going to still be the same number. So our assumption that it was minuscule is a safe assumption to make. We can keep the answer that we get for the solubility of lead. So our final answer is 0.000064 molar. Right? So this assumption is going to save you some headache and some trouble. All right, number 6 is similar. says KSP for ZnOH2, so let's write out the expression because that's definitely going to be handy. It's going to be Zn plus 2 to the first power, and it's going to be OH minus squared because I get 2 OH minuses. Wants to know what is the molar solubility in a buffered solution with a pH of 12.2. Alright, well they didn't tell us exactly what the concentration of this OH minus is, but we can figure it out. Alright, easiest way to do that is probably use the pH plus POH equals 14. So I go, alright, well what's the POH? It's going to equal 14 minus the pH. So I end up getting 1.8. Yeah. So now, alright, well how do I go from POH to OH minus concentration? Well, you got to remember that pH equals, POH equals negative log of the OH minus concentration. So we move that negative sign over there. We get rid of the log by doing 10 to the negative POH. I keep doing that. That should equal our OH minus concentration. So this is really 10 to the negative 1.8. And I'm going to leave it like that because that's only a few digits, and if I were to use a calculator, I'm going to get a bunch of digits there. So I'm just going to leave it like that. I use my smart graphing calculator. It saves my, brain a lot of work. So now it wants the molar solubility in this pH. So now we have the common ion concentration. It's going to be 10 to the negative 1.8, and that's going to get squared. Well, how much Zn are we going to get? We're going to get X amount of Zn, and we're going to get more OH as we add ZnOH. So it's really going to be plus, well, we're going to get twice as much than we do Zn, so plus 2x. Now, we're going to assume that this number is, again, tiny. We're going to assume that we can ignore it, that it doesn't exist, and we can come back and check to see if it's all right that we did that. So now we got to solve for x. So we get x equals KSP all over this number of 10 to the minus 1.8 squared, and I get my answer being 1.99 times 10 to the minus 13. So let's think about this. I had 10 to the minus 1.8, and I was going to add 2 times 10 to the minus 13. Think about how different those two numbers are. How much smaller this number is than to the negative 1.8. This is negative 13. That's like a million difference. So yeah, our assumption that this was tiny enough to ignore, totally valid. So our final answer is this right there. Boom. All right. 7. Just kind of a definition question. All right. It wants to know what is an assembly of a metal ion and a Lewis base is called a complex ion. All right. So like, let's say we got a metal ion in there and a Lewis base. Those are going to be electron donors. So like, I'm just going to make up oxygen. Let's say it was water. So what's going to happen is, here we got a positive ion, and it's going to make kind of a bond with those lone pair of electrons, and that's going to happen all around that copper with other waters or, whatever is interacting with it. So we get this thing that's called a complex ion because the whole thing is still going to have a charge, a +2 overall or whatever it is. This is going to be this weird complex ion looking thing. And that's pretty much the basis of what you need to know about that. So that's it, man. Grocery bags.